we're going to develop one of the most important ideas in physics and in the physics of energy, and that is what I call the work energy theorem. I think the book calls it the work energy principle, so it doesn't matter what we call it. It's just the relationship between work and a particular kind of energy. We're going to call it the energy of motion, or kinetic energy. So here's the situation we had, and earlier we worked a problem similar to this. If we have I'm just going to put a crate on wheels again, and we apply a force to it. Here's a force. This has a certain mass m, and we're going to move a certain displacement delta x. Okay. So now, if I'm going to say, I think in the problem that we worked earlier, I made the velocity of this 0, but it doesn't have to be 0, right? The crate could be moving along at a certain speed, and then I push on it and I accelerate it so that it goes faster. So what I want to do now is I want to develop a relationship between the work that I do and the result of the work that I do. Now, if this thing is moving along in this direction, and then I push on it with a net force, what is the result of pushing on it with a net force and doing work on it through a displacement? Well, the result is that it moves faster, doesn't it? And because it moves faster, it can do more stuff. It has what we're going to end up calling kinetic energy. And so what I want to do is relate how much work I do to how fast it's going at the end, to its speed. Okay, and that's what we're going to do right now. So, well, work is equal to force times displacement times the cosine of the angle between the force and the displacement. And let's just, to make things simple, let's just stipulate that this force and this displacement are in the same direction, which means that this is equal to 1, and we won't worry about it right now. Now, now this right here is a very special force. This force that's pushing on it right here, we're going to call that the net force, right? Remember the net force? And nothing's canceling it out. I mean, if I drew a free body diagram, I would have gravity, I'd have a normal force, but they're canceling each other out. Well, because this is on wheels, we're going to say there's no friction, there's no resistive forces. This is the only force acting in the x direction. So, and the displacement's in the x direction, so we're going to call this the net force right now. And so we have the net force times delta x. Now I want to get this in terms of velocity and stuff. So, well, what is true about the net force? What's the most important equation in all of physics? The net force equals mass times acceleration. Yes? All right. So now I can say, I can substitute in there. Okay, well, this is equal to mass times acceleration times delta x. But again, I want to develop an idea of, I'm going to relate how much work I'm doing to how fast it's going, or its speed, or velocity, or whatever. So what I'm going to do is I'm going to say, well, look, I know that the acceleration is a constant because this force is a constant. And so I'm going to use a kinematic equation that has acceleration in it. And I don't want to mess with time. So I'm going to use the fourth kinematic equation. Now this is kind of a proof, okay? So I wouldn't expect you to just pull this out of your head, instantaneously. Somebody messed around with this for a long time and developed this idea, and I'm just showing you the results of it. But what I'm going to do is I'm going to solve this equation for the acceleration, and then I'm going to substitute it in here. And let's see what we get. So everybody right now, in your notes, solve this for acceleration. You don't have to watch what I'm doing. To do it yourself. Solve for acceleration, and then substitute it in there, and let's see what we get. Do that now. So no peeking. So I'm going to do it. Acceleration. So 2a delta x is equal to, what have I got here? I got v squared on this side, and then I subtract this from both sides. V naught squared, I subtract it from both sides. So that's what I'm doing. Ooh, I'm getting close. I'm getting close now. I want to get acceleration by itself, so I can substitute it in there. So I'm just going to solve for a. A is equal to the final velocity squared minus the initial velocity squared divided by 2 delta x. Now I've got an expression for, no peeking, I said. Now I've got an expression for the acceleration in terms of velocity. Now let's see what happens when I substitute it in there. Do this yourself. Pay no attention. So this is mass times acceleration. Oh, but acceleration is v squared minus v naught squared over 2 times delta x times delta x. Now what I want to do is I want to simplify this. Delta x cancels out. Do this yourself. You don't need me. You can do this yourself. So this is equal to m times v squared minus v naught squared over 2. But this is kind of messy. Let's put the m in there and all that, and I'm going to get this into a final form that I'm going to really like. So this is divided by 2. That's the same thing as 1/2. And here's a mass. I'm going to multiply the mass in here and the mass in here. So this is going to be m v squared minus, and then now this 1/2 goes with this v naught squared too, right? And so it's 1/2. And then I'm m v naught squared. And we did it. Okay, did you get that far? Did you follow along? Or did you do it yourself? So all I did was screw around with algebra here. And I just said, okay, took the second kinematic equation, solved it for acceleration, substituted it back in here. Oh, delta x cancels out. Woohoo! And then you get this expression. And then I just kind of massaged it and expressed it like this. Now this right here is very interesting. I did work. Now let's say the initial velocity was 0. V naught is 0. If V naught is 0, then all I've got is this, 1/2 mv squared. And this is the work I did. So I did work. I used energy from my body or whatever, and I pushed on this thing. And the result of that, and because I pushed on it, I did work. And the result of my work was this, 1/2 mv squared. When I did work, I transferred energy from my body into the moving object. This is how much energy was transferred into the moving object. And this is the energy that the object has because it has mass and because it's moving. It is the energy due to mass and motion. And we have a name for that kind of energy. It's called kinetic energy. Now how does our, I forget. Now our book abbreviates kinetic energy, and different books do it differently. This book abbreviates it with KE. So I'll try to remember that. My other book, my other physics book for my other class, it just uses a capital K for kinetic energy. But this book uses a KE. So I'll try and stick with this book. So the kinetic energy an object has, because it's moving and has mass, is 1/2 the mass times the velocity squared. Okay, now this is a big deal. This is the kinetic energy equation. Now, if an object has mass and is moving, this tells us how much work it can do. Like if a baseball is moving at your face, and let's say baseball is about 0.16 kilograms, and it's moving at, let's say, 40 meters per second, it's got energy, and it can do work on things. If you've ever caught a baseball or a softball, right, it smacks into your hand, right? It goes, it's doing work on your hand when it hits. It can do things. It can break a window. It can sprain your thumb. That's what happened to me. I was a catcher in Little League, and this big, huge monster of this sixth grader who'd been shaving for a couple of years by then. He was this mountain, and his name was Gabe Montoya, and I had to be his catcher, and he could throw a fastball like a man. And he did, and it messed up my hand. I sprained my thumb. So that baseball had energy, and therefore it could affect change. It could do things. And this is a measure of how much work it can do, because it has mass and it's moving. Okay. So here we have the kinetic energy equation. But look up here. So the work done by the net force, I'm going to call that work. That's the net work. The work done by the net force is the net work done. Now, this is going to make more sense when we have objects that have multiple forces acting on them. Okay, but look right here. See? Well, based on that, this is the final amount of kinetic energy it has. See, I pushed on it, but it was already moving. So this is the kinetic energy it has at the end over here. Like I push on it. So here's the crate right here, and it's whoosh. Look how fast it's moving now. All right, and so it has. This is the final amount of kinetic energy. So this is KE final. But I want to know, but the work done by the net force, it already had some kinetic energy. And I'm looking at how much energy was added by the work done. So I have to subtract from that the initial amount of kinetic energy. Okay, well, what is a final minus an initial? Well, this is the work energy principle, or theorem, is the work done by the net force will be exactly equal to the change in kinetic energy of our object. So if you look at an object and you look at all the forces acting on the object, you figure out what the net force is, and it's displacing through space, right? And you want to know how much work is being done by that net force. Well, that work done by the net force will change the kinetic energy of an object. Okay? Now let me ask you a question. Is kinetic energy ever negative? Let's look at our definition of kinetic energy. Can kinetic energy ever be negative? Why? You say, why? Right. Well, is there such a thing as negative mass? No. Now, what is a negative velocity? What does the negative mean when you have a negative velocity? The negative is mainly talking about the direction, right? But we're squaring this, and actually, when you square a vector like this, when you square a vector, because velocity is a vector quantity, isn't it? When you square a velocity vector, you're taking the scalar product of that vector with itself. Like if this would be v dot v. Well, this is just the speed squared. You don't have to worry about the vector nature of it. You just get rid of it. You just look at how fast it's going, the speed. Well, speed is always positive, and you're squaring it. Anyway, kinetic energy is always positive. Does that make sense to everybody? Has to be positive. Now, let me ask you this. Can a change in kinetic energy ever be negative? Can something lose kinetic energy? Can your K final be less than your K initial? Yes, of course. When you catch a baseball, what are you doing to that baseball? You're doing work on it. Here's my baseball, the official baseball of science. Okay, and here's my hand, and let's say it's moving, and it moves really fast, and it hits my hand, and my hand always has a little bit of give to it, right? Any baseball players in here or softball players?
I mean, I used to like years ago.
Okay, if you don't have a little bit of give to your hand, John, what happens if you don't have any give to your hand and you try to catch a ball?
Your hand. Oh, it hurts. It hurts a lot.
It hurts, right?
So it just doesn't go back like
Right. Right. If you held your hand right here and that baseball comes screaming in, bam! Ah! Oh, it's going to hurt. But you know what? Your hand's going to give a little bit. There's still going to be a little bit of displacement. What you're doing is you're taking the kinetic energy away. You're applying a net force to that ball with your hand, and you are taking away its kinetic energy. You are doing work. But look, what direction, look at the screen, what direction is the displacement? That way, right? The displacement of my hand is to the left, right? But what is the direction of the force that my hand applies to the ball? Because we're looking at the energy of the ball, not of the energy of my hand. So to the right, right? So as the ball comes in like this, and as I catch it, I apply a force to the right on the ball. But the ball displaces, as I'm catching it, the ball displaces to the left as I apply a force to the right. Well, the work done, right, work is equal to the force that I apply to the ball times the displacement of the ball times the cosine of the angle between them. Well, if the force I apply to the ball is to the right, but the displacement is to the left, what's the angle between to the left and to the right? 180 degrees. So you would say, well, whatever this force is, times whatever this displacement is, times the cosine of 180 degrees. What is the cosine of 180 degrees?
-1.
It's -1. So this is going to be negative work. So when I catch a baseball, I'm doing negative work on it. I'm taking away its kinetic energy by doing work. And when I say negative work, that means I'm just taking away that energy. Does that make sense to everybody?
Yeah.
Any questions on that concept? Stay with me. And if you're watching the recording of this, raise your hand, I really am looking around right now. Looking at your eyes, make sure you're awake. Stay off your phones. All right, so anyway, so that's kind of it right here. I mean, that's all I'm going to lecture on today. We have some problems to practice with, but let's just summarize that, we have the work done by the net force. I'll just make a little equation list here. The work done by the net force is equal to the net force times the displacement times the cosine of the angle between the force and the displacement. The work done by the net force will result in a change in the kinetic energy of an object. And the kinetic energy of an object is equal to 1/2 the mass of the object times its speed squared. You don't really care about the direction it's moving. It's just, mass times velocity squared. I mean, if this ball is moving to the left or to the right, if I go 1/2 mv squared, it has kinetic energy. Kinetic energy is a scalar quantity, no direction associated with it. This right here is called the work energy theorem. Now, in our book, it calls it the principle, but in almost every textbook I've ever read, it's always been called the work energy theorem. It's not that important, but if you take another physics class someday, I want you to have seen this. And so these are the big ideas of today. Any questions? That is all.